Okay. All right. So getting back to here, this is line 1. This instruction takes up 2 bytes. So without the use of any labels, I would have to manually keep track of that, right? So I have to basically keep track and say, this is using up location 0 and 1. Then this one will be taking up locations 1 and 2, 2 and 3. This doesn't take up any locations, but this one does. So according to my calculation, increment B should be using location 4. So later on, if I need to get back to this location because it's the beginning of a loop, that means I have to keep track of all of these locations and say, oh, let's go ahead and go back to location 4 in the entire RAM. Okay, that's the location I want to go back to. But you can see how tedious this can get, right? The next instruction is going to take up location 5 and 6. This only takes 1 byte, which is location 7. This takes 2 bytes, which is location 8 and 9. This takes up 2 bytes also, which is location A and B, because we are counting in hexadecimal digits. And so the continuation point, which is on line 10 here, is going to be at location C. But you can see how it's really a lot of work to keep track of which instruction is at which location in RAM, if I do not have labels. Okay. On the other hand, if I have labels, all I have to say is, at this point here, if the carry bit is set, I want to go to the label of continuation, which is here, which is a symbolic name of the instruction that is actually on line 10. So now I don't have to keep track of all of those locations by hand anymore. So this is the reason why we have labels in any assembler as a tool. So is that okay? Does everybody understand the rationale behind why we have labels? Because without labels, you would have to do all the counting, which is not a whole lot of fun. All right? So do we have any questions about how the labels are actually defined? Like in this particular case, how label L0 is really no different than 4 as a constant. Every time you refer to L0, it is saying, oh, you are specifying 4, okay? Well, then you might think, well, then what is the value? Well, the value is, if I choose to do some more initialization up here, let's say I want to do LDIC with 0. That will offset everything, right? So all the counting that I have done below this point, everything is off by 2 bytes now, which is a lot of trouble to update everything. But if I use labels, it's up to the assembler, right? The assembler will figure out all of the locations of the labels, and it will update everything automatically. So that is why we want to use labels instead of having to hand count the locations and hard code those locations into the jump instructions. So is that explaining why we have labels? Yep.
So the label doesn't actually take up a space?
No, labels do not take up a space. You can kind of look at labels as bookmarks in a book. So a bookmark is not a part of the content that you're reading. It's really just a handy way so that you can go back to a certain page really fast. So it's kind of like that. Any other questions regarding labels? Yep.
So I just want to continue my question.
Yeah, go ahead.
For example, line 1, load immediate to register A, and we jump to label ID, which is down there, and then we put a number. Right?
Yeah, so ID is a number.
0, but in our case, it could be different bytes.
Yeah, so we can actually finish counting this, okay? So this is CD, and then we have E, F, right? And this becomes location 10 in hexadecimal. And this will take up location 11 and 12. And then this will take up locations 13 and 14. This will take up location 15, 16, 17. This will take up location 18. Now, I might have missed something along the way. Okay, that's the whole reason why we have the assembler doing it instead of me doing it, right? So this would be location 1A, 1B, and this would be location 1C. So according to this calculation, if I did it right, okay, ID as a label is actually defined to location 1D. Okay? So how do we check it? You copy and paste the whole thing. You go to the assembler. So we'll go find a window to go back to. Oh, okay, it doesn't go back to the drive, the Google Drive. And yep, there we go. So we go back to Google Drive, go to the assembler, and then we paste the code into the assembler and double check to see if I made a mistake counting. And if I did, it's actually a good thing because it shows the value of having the assembler to do all the counting. Because if you count by hand, it is very easy to make a mistake and everything is off, and so your program won't work. So I'm going to use the one with postfix expressions, but at this point of this class, either one will work just fine. So we go to the source tab, and remember, do not double click it. Okay, if you double click it, just escape, because if you double click it and you insert or paste over, it's going to paste everything over the same line, which is not what we want. I think I forgot to do Control C with this screen. Now we can do Control V over here. All right. So the assembler is doing its job, and obviously we have an unknown mnemonic here because there really is no such thing as JXI. The X is supposed to be a placeholder of one of the C, Z, SOL. So we'll just replace this one with JCI, for instance, okay? Because that's not the main point of our discussion right now. So we go to the assembler, okay? So the assembler, if you focus on columns U, V, and W, this is defining, label L0. L0 is defined to be at location 04. This is decimal, this is hexadecimal, okay? And we want to find out what is ID, right? The label of ID. So the label of ID is down a little bit, which is here. And according to the assembler, it is at location 1B. And I counted 1D, right? So I counted 2 extra locations for some reason. But you guys see why we have labels, right? Because if I did not have labels, I would have to do all that counting myself. So, did I answer your question?
What is byte 0?
Byte 0? Okay, so according to the assembler manual, it explains, byte something as an instruction to tell the assembler to reserve a byte in the memory of the processor and initialize that byte to whatever value you have expressed here. So this value here is expressed as a decimal number, but it will store the 8-bit representation of that value. So if I have byte 128, for instance, it will store that as 1 followed by 7 zeros as a bit pattern. So is that okay so far? Yes? Okay. Yep, go ahead.
Can you go back to the code, that last pad?
Uh-huh. Okay. We good? All right. Any other questions? Any other questions regarding this program? Yep.
You sent an email that we need to download the new processor file.
Yeah.
Do we need to do this lab again?
No. I'm just going to give you guys points here for that particular question as long as you have a reasonable answer. I messed up, for some really strange reason, I messed up the JSI instruction. The microcode of the JSI instruction has 1 bit turned off when it's supposed to be on. So, and I have no idea how that happened. I was trying to track it down, like, where did I make that mistake? And I could not even track it down. So anyway, so it's now corrected. The one on the drive is now correct. Okay. Any other questions? Has anyone ever wondered how the conditional branch is implemented? In other words, we have the JCI instruction, right? So it's different from the JMPI instruction in one major way. The JMPI instruction is always going to read the byte after the opcode and say whatever this byte specifies, okay, that is where I'm going to go to continue execution. That's the JMPI instruction. The JCI instruction says if and only if the carry flag is set, I am going to the location indicated by the next byte. Otherwise, I'm just going to execute the next instruction. Okay? So that is kind of like a conditional branch, like an if-then statement, except it is implemented in hardware. So has anyone ever wondered, how that works? Nobody. Does anyone care? I do. So there's no escape because I care. We're going to talk about it. All right. So we'll go ahead and write a very simple program to kind of just experiment with the conditional branch instruction. We'll just pick JCI, okay? Because the carry flag is bit 0 of the flags register. It's easy to visualize and keep track of that one. So to make it happen, okay, to make the carry flag either a 1 or a 0, we're going to do a compare instruction, okay? So we'll do LDA with 3, LDI B with 2, okay? And then we do a compare instruction. So if I compare in one direction, the carry flag is going to be set. If I compare the other way, the carry flag is going to be cleared, okay? So we'll just say that we want the carry flag to be cleared. So that means we want to subtract B from A because 3 minus 2 does not require a borrow. And as a result, the carry flag is guaranteed to be 0 after this. And then we have a JCI instruction here to go to some particular label. We'll just call this label 1, okay? We have one halt instruction here, and then at label L1 we have another halt instruction. So that means this program doesn't really do anything particularly useful because it's going to halt either way and there's no real computation because compare does not actually store the result of the subtraction. So the entire point of this program is to illustrate when we perform the JCI instruction, why in this particular case it is not going to label L1 and instead it is going to the halt instruction on line 5. Is that okay? Does everybody understand what we are about to do or what concept I'm going to demonstrate next? Okay? All right. So we'll Control-C, Control-A, Control-C, switch back to the assembler, and overwrite only column A. So look at the entire column A, clear the whole thing, and then just paste the code into here. Make sure there's no error. And then you go to the RAM file tab, and then click File, Download As, and you can choose either one, comma separated versus tab separated. They both work. And I'll just call this one, I'll call this JCI, okay, JCI.csv. And then we have to go back and restart the simulator. Okay, and then we'll reopen it from, all right, so where's my CISP? Oh, it's under Documents, cisp310, and this is text processor. Nope, that's the wrong one. I think it's just processor. There we go. All right, there we go. And it looks different from yours. So I don't have the latest one here either. But it's okay. It's sufficient for what we are doing. So we'll go ahead and load the program into RAM. It's called JCI.csv. And we want to single step through this program until we get to the JCI instruction. And then we'll go ahead and kind of explain more in detail. So this is what I want you guys to do. Whenever you have a question like, how does the LDI instruction get things done? Load a program, sample program, like this, and single clock it. Okay. When you single clock, you really need to kind of look into the control signals to every single component and understand how an instruction works. Okay. But in this case, our main focus is not the two LDI instructions nor the compare instruction. So we can just control T or single clock until we get to the instruction that is actually what we want, okay, what we want to look at. And that instruction is at location, let's see here, location 5, okay? So that means I don't really have anything to do, or I don't have to stop and look at things until the program counter, which is down here, until the program counter is 05, okay? So I just do a control T. Control T is the safest way to do it. Control K, depending on your clock rate, it can be going very fast, okay? So now the program counter is 05, but we are really just about to execute the previous instruction. Because remember, the program counter gets incremented when we perform the decode cycle, which is the second step of executing any instruction. So at this point, we are only at the decode phase of the instruction right before the JCI instruction, which is the compare instruction, okay? So we still have a few clocks to go, okay? And I think it's about time, okay? So we know this is about time. There are two reasons, okay? One is the instruction register is now enabled, which means we are about to overwrite the instruction register, which means this has to be the fetch cycle. Okay, there are no other places in the processor where we're going to overwrite the instruction register. This only happens when we are doing a fetch cycle, which is the first cycle of the execution of an instruction. Are we good so far? Okay. So where are we going to grab a byte to overwrite the instruction register? The program counter tells us, oh, we are going to location 05, which is our JCI instruction, to overwrite the instruction register. So now it is overwritten, and then we are going to decode it at this point, and you will see the program counter incrementing to 06 at this point. Okay? So question, big question. How does the program counter get incremented? First of all, how do we know that it is going to be changed? Incremented or not, why do we know that it's going to get changed? Because the enable pin is a 1. Okay? Next question, if you know a register is going to be changed, you have to automatically ask the next question. How are we updating it? Okay? Who is supplying the data or the bit pattern to update this particular register? So you track the D port back to the multiplexer. This multiplexer has a select of 0. So that means input 0 is going to the output of the multiplexer. You track down input 0. It's coming out of the adder. Okay? Now the adder can add 0. Okay? In other words, it can make no changes to the result. But you have to look at this pin here. This is carry in. It is a 1. So that means we are actually adding this 1 to the program counter itself, so that whatever is going back to the program counter is program counter plus 1. So the program counter currently has a value of 05. So that means when I have a rising edge, which is the next control T, the program counter will increment to 06. Is that okay? But who is controlling all of this stuff here? Who is telling the program counter to auto increment? So if you scroll down just a little bit, you will see that we are on the second slice of the first few slices of the ROM. This slice is known as the decode cycle. So the decode cycle has got two things to do. One is decoding. The second one is to increment the program counter so it's ready for the next byte, because we have just grabbed one byte and put it into the instruction register. We don't need that location anymore. We want to get to the next location. So is that okay? Does everybody understand why we are incrementing the program counter? Because whatever the program counter was pointing at is now in the instruction register already. I don't need to point to that location any further. Is that okay? All right. So the second thing a decode cycle is going to do is to decode whatever is already stored in the instruction register. So you can see the instruction register has 44 in hexadecimal right now. So the decode cycle is going to take that and update the microcode pointer so it becomes 440 in this case. So we have explained this decode process a few times already, so I'm going to assume that you guys remember how that works. Is that okay? Okay, all right. So Control T, and you can see how, okay, one more time. You can see how now we have just performed the decoding. So the microcode pointer is now 440, and that 440 versus the 44 is no coincidence. Okay, it is definitely by design, going to that location. But now the question is, well, we look at location 440, it is 188.0.0.0.6, okay, which is the JCI instruction, okay? What is it going to do now? Well, you have to look at all the registers and look at the ones that are going to be updated to understand how this works, okay? So we scroll back up and we look at all the things that are enabled at this point. We can see that not too many things are enabled. The register bank, the input is not enabled, the output doesn't seem to be enabled, but the program counter is enabled. So the program counter is enabled. Now the question is, how are we going to update this? That's the question, right? So you look at the program counter, and you look at the data port or the data port of the program counter. It's coming from the multiplexer. The multiplexer is selecting input 0, and this is input 0, and it comes from the adder. The adder has a 1 to add to it, and that's why we are skipping that byte that specifies where to go. In other words, we are not branching. We are just going like, ignore that branch, we're just going to continue to execute. So now you have to ask a deeper question. The deeper question is, why did it specify 0 instead of 1? Because PCMux does not come from the ROM itself. PCMux is coming from another part of the circuit. Okay? So now we need to track down PCMux or PC multiplexer. So we can highlight it. Okay? Just use the poke tool to highlight it. So you can see PCMux is also used here, and it is actually the output of this particular multiplexer. Is that okay? So now we look at this multiplexer here and ask, why are you outputting a 0? Because that output turns out to be our PCMux, which controls this particular multiplexer here. This multiplexer is instructed by this wire, which is called PCMux, because it's a multiplexer that controls a multiplexer. So PCMux does come from ROM, okay? And it specifies 0. What is it going to do? It's going to take input 0 of this multiplexer and connect it to the output. All right, so we track down input 0 then. We track down input 0, which is this wire. And where is that wire coming from? It's coming from a splitter, but before it splits, where is it coming from? You can track it down. It's coming from the flags register. Okay, it's coming from the flags register. It's bit 0 of the flags register. What is bit 0 of the flags register? The carry flag. So we are using the carry flag to feed to PCMux, basically. And PCMux is what is controlling this particular multiplexer, so that we are using the auto increment mechanism to change the program counter, which basically means, oh, just ignore the byte that the program counter is pointing at right now and just move on to the next one. In other words, we are not branching. We are just skipping the JCI instruction. Is that okay? Are we doing okay so far? So, yep, question?
How can you tell that that's the original piece? That this PCMux
Mm-hmm.
is the original of this?
How can we tell?
Because they're both labeled the same, right?
Yes.
That one's Lux and this one's
So all the tunnels are connected. All tunnels of the same name are logically connected. So when you click on this one, when you select this one, you can see how this one is also highlighted. Because they are really the same node, they're the same electrical connection.
right. How can you tell? You said that this one stems from that one. How can you tell?
How can I tell?
You said you were tracing backwards, right?
Yes. Uh-huh.
And you went from this one to that one
Yes.
by just clicking on.
Yes, by clicking it and also by kind of reading around the screen, you can find the other tunnel. So it's still, for people who are not familiar with the processor, it will take you a little bit of scanning to find it. But clicking on the wire to make it highlight it, will help you visually locate, where is PCMux connected to. So you still kind of have to manually, kind of go through the whole thing and find out, where PCMux appears. Am I answering the question, or was that the question? How do we find out where PCMux is connected to?
But it's also connected to the mux above it.
Yep, it does.
So how do you know that
It is.
this one as opposed to that one?
It is the same. They are all the same. If PCMux changes to 1, it will change this one to 1 as well. But it's irrelevant at this point, because if PCMux is 0, that means I'm not even paying attention to input 1, and this wire is only impacting this particular multiplexer. So I can kind of ignore what it's doing here. Is that okay? All right. Okay, so this picture shows you why. Oh, yeah, go ahead. Okay, so how do you determine the value of PCMux? You can see how PCMux is the output of this multiplexer, right? So now the question is, who is controlling which input of this multiplexer connects to the output of the multiplexer? That turns out to be this wire. So this wire, which has a tunnel name of PCMux, is controlling which input of this multiplexer goes to the output of the same multiplexer. So when we select 0, 0, 0 as the selection, then input 0 connects to the output pin. So now what we did was we tracked down input 0, which basically is bit 0 of the state of the flags register. And bit 0 of the flags register is the carry flag. We know that because we looked into the ALU in the previous class. So is that okay? How we kind of track down everything, in Logisim? Yes? No? Yes?
Why are there constants attached to the PCMux? Why are the constants 0 and 1 attached to the?
Okay, that's a good question. So the question is, why do we have constant 0 going to these two inputs of the multiplexer and a 1 going into this particular input of the multiplexer? Because certain times we do not want PCMux to be dependent on one of the 5 flags. We want it to be a 1 for sure, or we want it to be a 0 for sure. So that's why we plug the constants into those wires. Huh?
What type of scenario do you make
Okay, that's a good question. Okay, so the question is, why do we want PCMux to be a 1 sometimes, and why do we want PCMux to be a 0 other times, instead of depending on a flag? Is that kind of what you're asking? Okay. So when you look at PCMux, which is here, when PCMux is a 1, it is using input 1 to update the program counter, right? So input 1 comes from this particular multiplexer, and there are 2 wires coming into this multiplexer. Let's click on those 2 wires and see where they go. So we'll click on the left one. This wire comes from a register. In other words, there is a way to directly update the program counter using one of the 4 registers. So that means you can compute the actual address of where you want to go to continue execution, which is really cool, okay? It's kind of like you cannot do this in C and C++. There's no way to do it in C and C++ because you cannot continue execution based on the result of a calculation. It goes a little bit beyond pointer arithmetics, where you can only control what you're accessing, but this allows you to say, oh, I want to continue execution over there. But where's there? Oh, it's based on the calculation that I did earlier in this register. Okay? What about the other wire? So the other wire goes here, and that's your data pin. In other words, there is a way for me to use a RAM location to directly update the program counter. Now, why would I want to do that? because the JMPI instruction needs that. How does the JMPI instruction work? The opcode takes up 1 byte. What is the next byte? What is the byte following the opcode? It specifies where you want to go. So that location is in RAM. It's pointed to by the program counter. So that's why we need this path here, so that there's a way for me to take 1 byte from RAM and use that byte to update the program counter. But both of these operations require PCMux to be 1. What about, when do we want PCMux to be a 0? All of the other instructions. Just move on to the next byte. Auto increment. So is that okay? Okay, all right. All right, so I'm just going to continue execution here. In other words, I'm going to control T again. So when I control T again, this program counter is going to be 07, okay? Just like that, now it's 07. Which means if you look at the assembler, we are now at location 0, which is the halt instruction right after the JCI instruction. Is this where we are supposed to be when the carry flag is cleared? Are we convinced that this is where we want to be if the carry flag is cleared? Because we did not branch. Is that good? All right? Okay. So now what we'll do is we'll flip the 3 and the 2 so that we are forcing the carry flag to become a 1. Okay? And then we'll see how this time we are actually going to branch. But before we move forward, is the current state of the processor okay? Or are there any questions regarding what we have just seen in the processor? There's a lot of details, okay? I'm not counting on you guys to remember all of the details. What I am counting on you guys to do is to understand the process of tracking down how instructions work. That is the most important part of this lecture, is for you guys to learn how do I track down the components of the processor so that I can actually understand, how an instruction works. So do we have any questions regarding that? No? Okay. For the most part, if you can solve a maze puzzle, you will be able to do this. It really boils down to a question of proficiency. How quickly can you track down those signals? There's no easy way to get around it, okay? If this is the first time you see this picture and I ask you, where does PCMux connect to? You're going to have to spend some time to figure it out, because you really have to kind of search through the entire picture to find out, okay, is this PCMux, is this PCMux, and so on. But if this is the 20th time you do this, do you think you still need that much time to find out where PCMux is coming from? Nope. So it boils down to you have to do it. The more you do it earlier, the easier it gets later on. Okay? All right, so now we're going to change the program a little bit. The way I'm going to do this is I'm going to click the clock line so it's low again. Then I will reset the processor. This button here resets only the processor. It does not reset RAM, which is kind of cool because it doesn't mess up the program that you already have loaded into RAM. So I'm just going to click this one here. And you can see the RAM content is still intact. So what I'll do is I'm just injecting a 02 into here and a 03 over here to force a carry bit to be a 1. Because I'm keeping the subtraction, which is A minus B, but this time A has a value of 2 and B has a value of 3. 2 minus 3 is going to need a borrow, which is our carry flag. Is that okay? Yep.
Can you do the same thing with a compare B plus?
Say that one more time.
If you just change the instruction, compare AB to compare B.
Yeah, you could do that. But that takes a little bit more bit manipulation, which I don't want to do. This one is really easy to see, just like exchange the values. But you were right. Instead of using CMP AB, which is subtracting B from A, I could change that to CMP BA, which subtracts A from B. That would accomplish the same thing. But then I wouldn't exchange the values. Yep. Okay, so same thing. So we are going to control T until we get to the 4-4 location, okay? Okay, so at this point we are in a fetch cycle, okay? We're in a fetch cycle right here. How do we know we're in the fetch cycle? Because the microcode pointer is 0, 0, 0. We're in the fetch cycle. Very good. And where is it fetching from? What is the program counter pointing to? The program counter is barely visible from here. Now it's visible. The program counter is pointing to location 05, which is where the 4-4 is, right? So if I control T, it will first put the 4-4 into the instruction register, like that, okay? And then if I clock 2 more times, it's going to put the 4-4 and decode it into the microcode pointer, which is 440. Okay, up to this point, we have done this already, okay? We have done all of this already. And it's already decoded, so we are now ready to execute the microcode corresponding to the JCI instruction, just like last time. There's one difference. The carry flag is a 1 this time, not a 0, okay? So what we do is we move up a little bit, and we can observe that not only is the carry flag a 1, a few other flags are 1s as well. This is C, this is 0, this is the sign flag. Does it make sense that the sign flag is a 1 when we subtract 3 from 2? Yeah, because 2 minus 3 is -1, and as -1, the sign bit has to be a 1, okay? This is overflow. Does it make sense that the overflow is a 0? We subtract a non-negative value from a non-negative value and end up with a negative value. Can that happen? Yeah, it can happen. So it's not overflow. The last one is L. Okay, bit 4 is L. Does it make sense that the L flag is a 1? The L flag is a 1 if and only if register A is less than register B, interpreted signed. Okay? What is 00000010 signed? What is the signed interpretation of that bit pattern? 2. What is the interpretation of 00000011 signed interpretation? 3, right? Is 2 less than 3? Yes. So the L flag is 1. Makes sense. Is that okay? But out of the 5 flags, we only pay attention to 1. Which one are we paying attention to? Let's ask PC Mux Mux, the same as last time, right? So PC Mux Mux is still the same as last time, which is 0, 0, 0. So what that means is we are telling this multiplexer to connect input 0 to the output. This is where the difference is. Because input 0, which is our carry flag, was a 0 last time, it is now a 1. Okay? So this one gets sent out to PC Mux, and then PC Mux is connected to the select of this particular multiplexer right here. So this time we are selecting input 1 to connect to update the program counter. That is why we are not incrementing anymore. Is that okay? Well, if we're not incrementing, what are we using to update the program counter? Let's check out this multiplexer here, this one here. This multiplexer has a select of 1. We can see it is a 1 here, but we also understand why it is a 1. This is a AND gate, but it is ANDing PC Mux and the negated version of register output 0 enable. Register output enable is a 0. We can see it even from here. So that means we are negating this 0, so it becomes a 1 before it gets to the AND gate. This one is a 1, so we have 1 and 1, and the output is a 1. So regardless of the reason, we are selecting input 1 to connect to the output for this particular multiplexer. So where is input 1 coming from? This is input 1. It connects all over the place because it is coming from the data port of RAM. Is that okay? Now, as soon as you know that something is coming or connected to RAM, you have to automatically ask 2 additional questions. 1, is, are we reading from RAM or are we writing to RAM? Okay? So we can only answer the question by looking at the control signals going to RAM. And according to this, we are reading from RAM because RAM load is a 1. If you do not understand why RAM load is a 1 means we are reading, then you really have to review the component documentation itself in LogiSim, okay? Because we have been talking about this for a few classes already. RAM is definitely selected, it's paying attention, okay? So this data port is outputting the content of whatever is addressed in RAM. So that brings me to the second question that you should be automatically asking. Who is specifying the location that we are reading from? So to answer that question, you track it down, right? You track down this A pin here. It goes into a multiplexer. This multiplexer says, I'm connecting input 1 to the output. All right, let's track down input 1 then. So you track down input 1, and not surprisingly, where is it coming from? The program counter. Because right now the program counter is pointing past the opcode, which is 44. The byte right after the 44 specifies the location of where we're supposed to go when the carry flag is in fact a 1. So this is how the conditional branch works, okay? Depending on the flag, it has two choices. One is auto increment, which basically just skips that location and say, we are just moving on to the next instruction. No branching. The other one is to say, oh, whatever the byte after the opcode is specifying, we're going to go there. Is that okay? So in this case, where is that location specifying? That location, that byte specifies, let's go to location 08. And let's go back to the assembler and find out where location 8 is really talking about, what we're talking about here. This is location 08 because column W is the hexadecimal version of an address. What is that? That's my other halt instruction, which is proper in this case because the carry is going to happen because I changed these two values. So is that okay? Does that explain how conditional branch works in this particular processor? Is that okay? Are there any questions about how to track down how a particular opcode works? In a way, it's easy to study for this class at this point. In a way, it is also very hard to study for this class at this point. Okay? The easy part is basically saying the processor is self-documenting. I mean, it's completely laid out, okay, as long as you understand how each individual component operates, and you understand how to read the ROM content, convert the hexadecimal values back into binary values, or really just to track down the wires, okay, then you already have all the tools to understand how the instructions work, okay? So that's kind of the easy part of why I said from here on it is easy to study for this class. It is also difficult to study for this class at this point because if you're used to reading books, there are no books to read. Okay? So then you have to ask your question. When you go to work as a software engineer, as a developer, as a computer engineer, do you think that you have books on everything that your boss is going to ask you to do? Okay, the first thing you're going to do as a software developer is you're going to have to debug somebody else's code that has been sitting around for a while and it is buggy. Okay? Do you think you will find a book to explain that? Do you think the previous person who wrote that driver that you're going to have to fix left behind sufficient comments so that you can follow the logic of that person? It's a big maybe. Okay? Do you think that documentation, that comment, is actually correct? It is accurately describing the driver code that you are seeing? That's another big maybe, which boils down to no, you cannot rely on any published information. You have to go back and figure out everything by yourself. What about the programming language? Do you think your boss is going to give you a project based on what programming language you're already familiar with? No. One day your boss would just come in and go like, Tech, I need you to write this program in Python. But boss, I hate Python. It has no curly braces and I cannot get used to it. Well, now you're going to get used to it. That's going to be what's going to happen. So you kind of have to develop the mentality and also the technique to look at something and figure out how it works. Okay, I'm more than happy to help you, along with this process. Okay, especially during the lab time, if you can show me, I don't really quite understand, how this particular clock happens with this particular instruction. I can help you, track down all the signals and explain to you how it works. And trust me, the most tricky instruction of the entire processor are the conditional branch instruction, and I just explained that. The rest of the instructions are really not that difficult. I mean, they're fairly straightforward by comparison. Okay? So are we good so far? Yep.
Question number 2 in the lab.
Say that one more time.
Question number 2 in the lab.
Question number 2 of the lab. Let me check it out. So question number 2, is that the one? Yep, okay. So we want to do a preview. And question number 2. All right, so what about this instruction? Okay, so this instruction, okay, so let's look at the code and look at the question, okay? The code says compare AB, JCI to L1, JMPI to L2. And then the last paragraph is the actual question. The earlier part really is kind of description of, the general scheme of things. If execution continues at label L2 right after the code, so we are actually performing the JMPI instruction, and assuming that L1 and L2 are defined at different addresses, because somebody can argue and go like, well, if they're defined at the same location, I wouldn't be able to tell anything, right? So let's say they're at different locations, right? What can we conclude about registers A and B? Okay, and you're given some choices here. You're given 5 choices. So first question is, if I am at label L2, okay, right after this block of code, do you think the carry flag was set or cleared? The other way to look at this question is, if the carry flag was set, would I end up at label L2? No. Where would I be if the carry flag was a 1? I'll be at label L1, because JCI L1 says, if and only if the carry flag is a 1, continue to location L1. Okay. Well, since I specifically said that we're at L2, so what can you conclude about the carry flag itself? The carry flag is a 0. Okay. If the carry flag is a 0, and all of these apparently are comparisons, right? So the carry flag pertains to what type of comparison? Signed versus unsigned. Unsigned. Very good. Okay. So we can now cross out quite a few items, right? Because all the int stuff, cross them out. So we are now down to the first versus the second. The first one says, A is less than B. Wait, if A is less than B, then the carry flag would be set. And we would be at label L1 and not label L2. So by crossing out all the impossible choices, I don't even have to reason out why it is the second choice, because it's the only one left. So is that okay? But this means you have to connect concepts back to a binary comparison and the meaning of the flags. This class is not compartmentalized, okay? Well, okay, in a little bit, in a sense, yes, we are, okay, because I'm not going to use this processor to deal with double values. Yeah, that may not happen because it just doesn't have enough resources to do floating point number calculations. But other than that, okay, everything that we have learned from the beginning of the class, not maybe in registers, not in transistors, what a NAND 2 gate is, it is still important today because that is how we can explain the operation of an SR latch, which is a part of a D flip-flop, which is a part of a register, which is a part of the processor. Yep.
Just to clarify, I mean, even if you were still, even if you chose as a programmer that you were dealing with signed numbers, the carry flag could still be set.
Yes.
You have there's just no way in this question for you to know whether you're dealing with signed or unsigned numbers. Because the carry flag could be set either way.
That is, well, okay, but the only thing we can really conclude is A is greater than or equal to B when seen as unsigned values.
Yeah, okay, I definitely understand that. I just wanted to make sure the carry flag would still be set.
Yes.
Even if it's an unsigned, even if it's assigned.
Because the comparison is completely blind to signedness of the values. It just performs. Do you guys remember the how we turned the adder into a subtractor? And that circuit has no understanding of whether something is signed or not, right? All it does is to give me a whole bunch of ands and give me a bunch of ors. We connect those in a certain way, and that's the result. Okay, they're all logical operations. So the adder or the subtractor really does not care whether you're dealing with, signed versus unsigned, operations. The flags, on the other hand, does. Okay, because the way we define the carry flag, which is K8 in this case, is the carry or the borrow of the two numbers. Okay, so that makes sense. Okay, the sign flag is the most significant bit. The overflow flag is defined in its own way, and then the L flag is the exclusive or between the sign and the overflow flag. Those definitions are signed versus unsigned sensitive. But the operation itself, compare, doesn't care. So when you're writing code in assembly, it is all the way down to the conditional branch instruction when you need to pay attention to are these numbers signed or not. Okay? When you're storing, it doesn't care. When you're comparing, it doesn't care. When you're adding, it doesn't care. It's only when you get to a conditional branch, because you need to know whether something is less than something else or not, then you have to know, oh, should I use the C flag or should I use the L flag? That's the only time, which is entirely different compared to C and C++, because in C and C++ or any strongly typed programming languages, guess what? The first time you declare a variable, that is when you say whether it's signed or not. When you compare, the compiler automatically remembers, oh, these two numbers are unsigned, I'm going to use the carry flag. The compiler makes that decision for you. In assembly language programming, the compiler doesn't care. The assembler does not care. Okay? It's only when you need to do a conditional branch, then you have to decide, wait, are these two numbers signed or unsigned? Can they go negative? Then you have to choose, should I use the carry flag or should I use the L flag? So it's a very different kind of mindset, translating code into assembly because of that. So are we still okay at this point? Everything is good? All right. Okay, so now that we are done with this lab here, okay, let's go see what is next. We are pretty much done with the volume architecture and memory at this point, because you can see how we are done with the last step here. This slide here is really just just my suggestion of how to study at this point, which is something that I have talked about already. Okay, so you really should read this if you have some question of what should I do to study for this class at this point, now that there's no text, no modules whatsoever. Okay, you basically have to look at the processor architecture itself, because it is self-documenting. But when you look at it in a static way, it's not going to help you a whole lot. You have to write some sample code, test it out, single clock, okay, freeze the frame, look at what registers are enabled, how it is getting updated, who is driving the address bus of RAM, who is taking the data back from RAM, and so on. That is how we study at this point. Yes?
Do you have any recommendations in terms of guidelines of what sample code to write to test it?
It depends on just which opcode you want to understand. So you would design a very small chunk of code around the instruction that you want to understand. So LDIs are pretty much standalone, okay, so they don't need any setup. But the conditional branch instructions, you can actually force values into the flags register. So in a way, they can stand alone as well, okay? The increment instructions are standalone. The decrement instructions are standalone. So most instructions are fairly standalone. You can just test it by itself. Okay. All right. So I'm not going to go over this module because it really is just talking about how to study for this class at this point, which I have already talked about earlier in this class. So we're going to continue and go on to the good stuff here. So the good stuff is, what is the connection between cisp310 and this class? Other than, you have to understand the opcodes, because of the notation that I use in C. So the question now is, if I give you a chunk of code in C and C++ or C++, without the object-oriented part, can you translate it into assembly code? That's the question. And is there a systematic way to do it? So that's what this slide is about, this module. So let me just give you kind of like the forest view first. So the first thing we do is deal with the C control structures, which will be the conditional statement, if, okay, the loops, the two kinds of loops, which is do while and while loop in C and C++. I'm not even going to bother to talk about the switch statement, okay, so there won't be any talking about the switch statement. And the for statement, for the most part, is really a glorified version of the while statement, so I'm not going to talk about that either. So it's a fairly easy kind of slide to go over. The next one talks about how to call and how to return from subroutines. Okay, in C and C++, it's pretty easy, right? You have a definition of a subroutine, and let's say it's F, okay? And then in main, you just say F, open and close parentheses, depending on whether you have parameters or not. Pretty easy, right? When the subroutine is done, it always knows magically where to go back to. So in cisp310, you don't have to think about that. It's like, how does this subroutine know where to go back to continue execution in the caller? In this class, we'll know exactly how. There's no mystery anymore. Okay, so in a way, if you look at cisp310 and go like, this is really cool, it's so magical. This class is demystifying everything. It's like, oh, there's no magic anymore. There's really no pixie dust involved, in a C program. There's no fairy inside the computer. This is so boring. I want to change my major. We'll talk about how to return a value, okay? So in C and C++, you can define subroutines that can return. I'm only going to talk about how to return a scalar value, which is basically an integer, a float, a pointer, that sort of thing. C can actually return a structure, but that's a little bit too involved, so I'm not going to get into that. This is a lot of fun. How do we pass parameters from the caller to the callee, okay? And how do we deal with local variables, okay? The concept seems to be pretty simple until you throw recursion to your program. Then it's not so simple anymore. It's like, it seems like every invocation of a subroutine has its own parameters and its own local variables. How does that happen? Okay, so that's kind of be what we'll be doing for the rest of the semester, and we will be writing programs, okay, to utilize all of these concepts. So for today, we got about 10 more minutes. And this is where we're going to go. And we'll focus on just section C for now, okay? And when we come back on Thursday, we'll move on to section 4. So this time, we'll just go to section C. And I'm just going to highlight this because I'm going to talk about it. This is just a template, okay? So C is a placeholder of a condition. Now, that condition can be something very simple, like A is less than B. It can be something very complex. It can be anything, okay? I don't care what it is. It's just a placeholder. Block 1 is just a placeholder for what I want to do when condition C is true for this conditional statement. And block 2 is just a placeholder for what I want to do when condition C is false. Okay? Are we good so far? Okay. So now I'm going to present you something that Professor Fox, Professor Antos, Professor Hermele will frown upon. I'm going to say that chunk of code that you saw earlier, which is really clean, using parentheses and curly braces and stuff like that, is really functionally the same as that. Okay? Can you buy that? Can you buy that this block of code is really the same thing as the other one, even though this one involves the use of go-tos and labels and all kinds of stuff that you're not supposed to use in your other programming classes? Can we buy it? What if C is true? If C is true, not C is going to be false, right? If not C is false, I am not going to go to L1. I'm going to perform block 1. After block 1, what do? I go to L2, and L2 is right here. I skip block 2. In other words, if condition C is true, I will only perform block 1. Does that match the behavior of the original code? Okay. What if C is false? If C is false, not false is true, then I go to label L1. I go to label L1, which immediately starts block 2. When block 2 is done, I just kind of fall through to L2. Would that match the behavior of the previous code? Yes. So why do I do this? Why do I turn something that is structured, that is nice, that all of your other professors would like to see, into something that's ugly? Sorry? Because that's one step closer to assembly code. Because in assembly code, there's no such thing as else. Okay? This is structured programming. This is destructured. It is flattened. And that's because in assembly language programming, we only have conditional branches like if and only if the carry flag is a 1, branch. If and only if the L flag is a 1, branch. If and only if the Z flag is a 1, branch. That's it. There are no more conditional branches after that. Yes?
What's the difference between assembly language and machine language?
Okay, that's a very good question. And I can illustrate that difference with a very simple tool that we have seen already. If you look at the output, that's machine code. Just a bunch of zeros and ones, in this case encoded into hexadecimal. And when you look at the source tab, that's assembly code. So assembly code is slightly more friendly to people. So we write code in assembly code, then the assembler will translate that into machine code, which eventually is what the processor is going to see. So that was a good question. All right, so getting back to our slide here. Okay. If there's no else, you can simplify a little bit. So if you have a conditional statement like this that has no else component, then it just becomes something like this. Okay, kind of makes sense, right? You just skip over if the condition C is false. What about pre-checking loop, which is otherwise known as a while loop? So the while C do block 1 thing translates to something like this. Does that make sense? Well, let's check, okay? The thing about the pre-checking loop is the condition can be false to begin with. Then you do not even perform one iteration, right? So now you ask the question, can this one do the same thing? If the condition is false, then not false is true, then we go to L2 and just continue execution with whatever is after that. Oh, okay, so we can skip even the first iteration. Cool. If the condition is true, do we perform an iteration and then go back and check the condition again? Because that would be the expected behavior of a while loop. So if C is true, then not true is false. We are not going to label L2. If we're not going to label L2, we perform block 1, which is the body of the loop. And implicitly at the end of the loop, we go back to while, right? Go back to the beginning. Well, in assembly code, you do not have that implicit going back to the beginning. If you want to go back to the beginning, you have to spell it out. So we have an explicit go to L1 to continue the loop. And by the way, this is actually legitimate, syntactically it's legitimate C code. It's just that your other professors would not want to like to see you using go to and labels. But it is really the same thing as the other one. Yep.
Why did you use not C instead of just plain C?
Because this is more direct. This is actually more direct to use a not C here. Because if you say C, then you have to go to a label kind of right before the block 1, and then have another go to go back to go to label L2. So that increases the number of go-tos and labels. Yep.
Why don't the professors look down upon stability system?
Because it makes the undisciplined use of go-to and labels can lead to spaghetti code. So now the question is, why is spaghetti code such a bad thing, right? You can go to Wikipedia, and you go to the website like Google and find out why spaghetti code is bad. But it is something that you have to personally experience to understand. Okay, this is where education sometimes cannot really replace your work experience. What is the longest program you have written in cisp 360, 400, 430? A few hundred lines of code? 400, okay. So 400 lines of code is considered kind of big, right, in a class, okay. How long did you have to write that program? A week? 2? Just 1? 1 week? Okay. I have one single function that has 600 lines long. One function, okay? Yep.
Isn't it usually like not really efficient because, for example,
It's bad programming practice, but syntactically it's okay. The compiler can take it, right? So this is a 600-line function where it has a lot of go-tos, labels, and the use of global variables. Everything that is labeled bad, do not use, do not do this in the book, it's done in this particular function. And I had this misfortune to have to debug it. It was one helper function in the compiler. Again, I can't remember what it was supposed to do. That was actually one of the biggest questions is, what is this function supposed to do? We do not know. It has 600 lines in it. Okay? So normally you can look at the 600 lines and you can break it down, right? Okay, this is a loop, it contains a conditional statement, it contains another loop, and so on and so forth. Not when you have go-tos, okay? This particular program has a go-to inside a conditional statement that is inside a loop, inside a switch statement, inside another switch, inside another loop, to go right into the middle of another conditional statement, inside another loop, inside another loop, inside another conditional statement. That is what we call spaghetti code. So in the end, I basically just ditched the function. I figure out enough using a debugger, okay? I figure out enough of what the function was supposed to do, and then I just rewrote it from the ground up. There was no debugging it, there was no saving it. So the reason why we do not want to use go-tos and labels is not because they are inherently bad, but because it can easily lead to programs that are almost impossible to understand and track down and debug. Okay? I'll just say one more thing. I know we are out of time. I'll just say one more thing. What determines whether you are a good developer or a bad developer or inefficient developer? It is not the number of lines of code you can write per time, per unit of time. Yep.
It's how decipherable your code is.
Say again?
How decipherable your code is.
Because that determines how fast you can debug your code. Nobody can write perfect code the first time. I certainly cannot, okay? But I can find the bugs of my programs fairly quickly because I use good programming practice, so bugs are contained. They can be unit tested, okay? And once you figure out that this function is working 100%, you can actually count on it. Then you can debug the next level and then the next level. So effectiveness as a developer has to do with how you structure your code, what kind of discipline do you use when you structure your code, so that when you need to test your code, when you need to debug your code, it is fast, it is efficient, and later on, if you need to extend your code, it is also easy. Okay, so that's all I'm going to say today. There's no lab for tonight, no new lab for tonight. I think the other lab is still active, because it's due in a week. But there are no new assignments for tonight, which means tonight's lab is a perfect opportunity for you guys to play with all the different instructions in LogicSim, single clock through those instructions and figure out how they work. Yes? The next exam, so this is week 8 or 9 or so, week 9. So we have another 2 weeks before the next exam. So next Thursday we'll go over a practice test, and then the Thursday after that. So 2 Thursdays after this Thursday.
One more, right?
I'm gonna give you an answer that you're gonna hate. Read the syllabus. It's in there. Yes, surprisingly, yes. Yes, we have 2 exams and 1 final.
I just want to make sure I got the date.
Yeah.